This is an FRQ question from 2009 AP Calculus. So let's see how we can solve this. For question A, we are asked to find the area of R. And to find the area of R, we can separate the area into small rectangles. So let's draw that on the graph. So this is a small rectangle, and we draw a second one, and we draw an infinite number of rectangles. So this is the logic of integral. So this question, we need integral to solve it. So R is the integral from the lower bound to the upper bound, and we can see on the graph the lower bound is 0, 0, and the upper bound is told by the question, which is 4, 2. So it is the integral from the two x coordinates, so from x equals to 0 and to x equals to 4. So R equals to integral have 0 and 4. Now we also need the height and the width of the rectangles. So in order to find the height of the rectangles, we just use the top curve minus the lower line. Then we will get the height for every single point. And we can see the bottom line is y equals to x over 2. So the upper curve is y equals to square root x. Then the height will just be the top curve, x square root of x minus x over 2. So that's the height. We also need a width for the rectangle, and that will be the dx. So we have integral of 0 to 4 of square root of x minus x over 2 dx. And we just calculate this integral. The antiderivative will just be 2 over 3 x 3 over 2 minus x squared over 4. And we have that from 0 to 4. And that just equals to 4 over 3. So question A is a 3-mark question. The first point is for the integrated expression. And the second point is for the antiderivative. And the third point is for the final answer. So you just need this, and this to get the 4 points. Okay, now let's look at question B. The region R is the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are squares. Find the volume of this solid. So in order to find the volume, we now need to erase all of these rectangles from question A, which is to calculate the area. So we need to have a cross-section of a square, which is perpendicular to the x. But we first draw a small rectangle, just like we draw the rectangles for question A. But now we just draw one so that we can clearly see what it looks like. Because the cross-section is a square, I just draw a square. It's like this. So that's the cross-section when you look through from the direction of x. And now we need to sum up all of the solid from x equals 0 to x equals to 4, just like how we do for the area. But now, since it's a solid, which means it's 3-dimensional, we need the height, the width, and the length. So we write volume equals to integral, again from 0 to 4. And now we need a square. So the square is just the height times the width. And that is the same as question A. We already have that. So that's square root of x minus x over 2 square. That's the area for the cross-section. And now we also need to consider the length. And the length is just dx. To solve it, we expand what is inside the bracket. So inside the bracket, it becomes x minus x 3 over 2 plus x squared over 4 and dx. And we just solve this integral. So this is x squared over 2 minus 2x 5 over 2 or over 5 plus x cubed over 12. And that is from 0 to 4. I will just substitute the values and we will get 8 over 15. So again, for this question, it is 3 marks. The first mark is for the integrated, second mark is for the antiderivative, and the final mark is for the answer. Okay, so now let's look at question C. Write but do not evaluate an integral expression for the volume of the solid generated when r is rotated about the horizontal line y equals to 2. So now let's just draw the line y equals to 2. That's a horizontal line which we will rotate around. And if we want to draw the final solid that's rotated the area about y equals to 2, it will be like this. Hope you can see it. So for this question, we need to use the washer method or the donut method to calculate the cross-section areas and sum those areas up from the start point or the lower bound, which is 0, to the upper bound, which is 4. So the donut method tells us to find the area of the cross-sections, and the cross-sections can be found by using the circle of the larger radius minus a circle of a smaller radius. So it is still volume equals to integral from 0 to 4. And now we want to find the area of the cross sections, which is like I said. So now let's find the areas of cross sections. Let's draw the bigger circle first and the smaller circle. So the cross section is just the area of the pink circle minus the green circle. So the pink area equals to pi r squared. And the pi, so the r is just the purple line to the bottom straight line. So let's write a equals to pi r squared, and the r is 2 minus x over 2. So pi 2 minus x over 2 squared. Let's use the same thing for the area of the green circle, which is area equals to pi 2 minus root x and squared. So now the cross section will just be the pink circle minus the green circle, and we need to sum them up. So it is pi times 2 minus x over 2 squared, which is the pink circle, minus pi times 2 minus root x squared, and that is the area of the cross section. And we can highlight it. It will be like this. So we just find the area of the cross-section. And now we need to sum the area up from 0 to 4. We also need the width, which is dx. And this question is also a 3-mark question. The first point is for the limits, which are also the lower and upper bounds, and the constant, which is pi. And the next 2 points are for the integrand. Okay, that's it. Hope you enjoy this.